In a way, the scenery was already set this morning, so symmetries is obviously one of the key words today. In a way, what I'm going to drag you through is a little bit of complementary to what David said in the morning, because we are not after Jordan symmetries, we are after the antisymmetric counterpart, the Lie part. And therefore, I invite you to share the symmetry view also with a second eye, the symmetric and the antisymmetric one. And it so happens that if you go into a quantum information processing, quantum engineering these days, there's a bunch of fundamental questions which really come as engineering questions, whose answers, however, drive you into some mathematics to be rigorous. And that's what I beg you to simply share with me today. And in particular, it's something like really an eminent Lie framework in which many of these questions can be answered. And it's more recent work with my master student, Markovian, who is so good that sometimes I try to call him Norbert. And it goes back to very nice work together with Robert, and it therefore also sets the stage for what he will be telling. Okay, so as I said, there's a bunch of fundamental questions by a quantum engineer which are left for a mathematician to be answered rigorously. And three of them I would wish to share with you. So to which extent can a quantum dynamical system given by, say, drift and control Hamiltonians be controlled? Or if you have an open quantum system, to which extent can it be accessed? To which extent can one quantum system simulate another one? And finally, and that's some new aspects also, to which extent can a quantum system be observed or sensed or tomographied? And all of this somehow are questions to be answered within a Lie frame. And I beg your pardon, because many of the questions we are going to answer is in terms of symmetries, and you have to count the symmetries, and you just have to count up to 2. So 2 will be the magic number of this talk. And of course, to make connected with the Lie frame, then all these types of questions can be settled by simply having a look into the symmetries of a system, the Lie symmetries, which I make precise in a couple of minutes. And therefore, very often, these questions can be answered just by the symmetries of the Hamiltonian, or in open Markovian systems, by the symmetries of the corresponding Lindblad-Kosakowski generators, and so forth. Okay, so setting the stage, who know me will have seen this picture several times. So we simply have a very operational and therefore Hanoverian, Wernerian, Ludwigian type of picture. So our quantum systems are input-output systems, and we have a control unit. In a semi-classical picture, you simply express your external degrees of freedom in terms of the internal types of control Hamiltonians, which you can piecewise constantly switch. That's these terms B. And then in an open loop, you simply steer this type of quantum system. So that's the stage. Usually linear systems go back to Kalman and Kalman filtering, Kalman matrices, and so forth and so forth. And bilinear systems come with the names of Djurcevic, Sussman, and Brockett. And the mathematicians among you might recognize the background here. So that's the famous Mittag-Leffler Institute in Stockholm, where, by the way, also the first Nobel ceremonies were held. Okay, so to start in a very simple fashion, you have your control system here expressed as a Schrödinger type of equation, where you have an unavoidable drift term and then some switchable Hamiltonians. They are switchable in time, and usually that's piecewise constant. Simply think of a digital waveform generator to connect with an experiment, and that's simply a bilinear control system. So it's linear in the system and in these controls with a drift term and switchable control terms. And that's, so to say, the extended Schrödinger equation to make it controllable. The bridge to Lie theory now is very simple. You take here the drift Hamiltonian, the control Hamiltonians, or A and B, and you simply form the Lie brackets until nothing further linearly independent arises. That's called the Lie closure, and that's the system algebra. System algebra is already very powerful, and the system algebra, of course, also has a commutant, so all matrices which simultaneously commute with all the A and all the B terms, that's the symmetries, that's natural constants of the motion, just as you would infer from quantum mechanics 1, whatever commutes with your Hamiltonian is a constant of the motion. That's, so to say, the first level of the picture. Already this is quite powerful because you see this is a Lie algebra here in finite dimensions, that's the rest of the talk in finite dimensions, and in particular in closed systems, this is either the full unitary algebra or proper subalgebra of it. If it's a full unitary algebra, then your system gives rise to a universal quantum computer, and therefore you immediately know that on such a computer you can implement all quantum gates. And the reachable set, that's a typical engineering question, given an equation of motion and an initial condition, what is the set of all states which I can reach? And they are simply on the group orbit of the initial state, and the orbit here expressed simply by a group, and that's simply the exponential here of this proper subalgebra of the unitaries, or the full unitaries themselves. Something which immediately arises here, if it's the full unitary group, this is the set of all matrices that share the same eigenvalues with the initial state, and therefore the reachable set under full unitary control coincides with what people in control theory call the isospectral set. So if the spectra coincide, then you know you can unitarily transform. So this is already very powerful also in engineering, because usually reachable sets are very difficult to come by. Let me now advertise a little bit of the notation to go to the next level. So if you vectorize your density operator, then these guys here really get a hat. The hat simply noting that's the commutation superoperator. And strictly speaking, this is exactly the adjoint representation, up to 1 degree of freedom, which we will come to later on. And now what I advertise to share with me is simply the point of view of taking the level of the adjoint representation, because the symmetries of the adjoint representation are more powerful than the symmetries just of the naked Hamiltonians. Okay, so that's our notation. And of course, these are operators, and still you would form the Lie closure, and therefore you get now to the second level, which simply is the adjoint representation of the system algebra, which you simply get by commutating the ad A's and the ad Bj's. Formally, it's the same thing. Yeah? It's now a closure over superoperators, but superoperators can be seen as operators. So no formal difference. And the symmetries are now those symmetries that jointly commute with the adjoint representation of the drift and all control terms. Just one level higher. And that's it. On this level, we will stay for the rest of the talk, and that's the appropriate one. And of course, that's here a master equation for the density operator, and therefore we are in the correct category to include dissipation terms altogether without changing the picture. And for the experts, since now here we have the commutator superoperator, which has 1 degree more than the mathematically adjoint representation just consisting of the structure constant, this trivial one simply gives you a unitality condition, and this allows you to incorporate unital and non-unital dissipative systems. Just as a side remark, So the commutator superoperator representation is physically the more appropriate one than just confining yourself to the structure constants. And this is even easier to calculate. Okay, and now we will stay with the symmetries of second order. And let's see what we can do with them. So if these symmetries here are trivial, then the system is fully controllable, and that's the nice result we had with Robert Thayer in 2011. And the reason for this, I'm not going to prove it, simply is the adjoint representation is by an automorphism the same as the tensor square representation. So you simply take a unitary gate and then you take U tensor U. And if you take U tensor U, you see immediately one non-trivial symmetry, and that's the swapping of the two gates. And therefore, in the commutant, you have the big identity and the swap operator. And Dünkin's classification simply tells you that when you are going to reduce this tensor square, you have, of course, an alternating and a symmetric part, an alternating square and a symmetric square. And if both of them are irreducible themselves, then the only group which is left is the unitary group itself, and therefore this gives you a universality criterion. And by an automorphism, you simply can take that into the adjoint representation, and structurally the same results hold. Okay, so that's the universality condition, which is a nice symmetry condition. By the way, it's the first full, complete, if and only if symmetry condition for controllability. If you were simply in the naked representation of, so without the AD, if you simply were in your representation of the dynamic system algebra, the commutant would be trivial, then this holds for every simple subalgebra, and therefore you would just be left with a bunch of candidates which you cannot differentiate. However, on the adjoint level, you can. And let me just show you the theorem with Robert. So if here we have drift and control terms, then this system is fully controllable, which means the naked system simply is governed by the n-qubit unitaries if and only if the commutant to the adjoint representation is trivial, here the big identity, and now the projection on the identity, which simply is the partial transpose of the swap. Okay, so that's this theorem. Let me simply also tell you that in a way, these are the branching diagrams we had with Robert. So that's SU16, and this is a cascade of irreducible simple subalgebras, which one can now which all come with additional elements in the commutant, and some of them are simply due to these guys being Cartan subalgebras. But let me not go into these details, but just jump. And now, you see, that's a controllability result, and in a way, a dual picture is an observability result. So what can you do when you start with an initial condition? And of course, if the unitary orbit is the reachable, or a sub-orbit of the unitary orbit is the reachable set, and you want to simply take the trace with a self-adjoint observable, you might simply go into the passive frame and simply let the observable now be rotating in the suborbit of the unitary orbit, given by the dynamics of your system. Then you can ask the dual question, which density operators can be differentiated. And just to anticipate the answer, which is in total analogy to the one we had with Robert, is simply such that now the commutant to the adjoint representation, together with the projection onto the vectorized observable, if this joint set has a commutant of dimension 2, then your system is fully observable. And that's the result I would wish to establish in a couple of minutes. That's a more recent result. But here you already see you have to count to 2. Yeah? We are in the adjoint representation. If the symmetries are limited to 2, then you have the full Monty. Okay, as an aside, we have seen these branching diagrams, and this, of course, just as a side remark, pertains to quantum simulation. So if you have 2 dynamic quantum systems characterized by their drift and control Hamiltonians, you may ask, can system A simulate system B? And of course, trivially, it's simply such that A simulates B if and only if the system algebra of system B is a proper or improper subalgebra of the simulating system A, just by counting the number of degrees of freedom in the dynamics. So in the branching diagrams, something on the left side, a child, can always be simulated by the parents, but not vice versa. And there are similar, more general results, which I would not wish to go into details. Let me just tell you a little bit how powerful this is by way of example. So if you have these types of spin chains, which are coupled by Heisenberg XX interactions, so that's the solid state notation, which probably I don't have to explain. And you have a spin chain with these white spins, which are passive, which cannot be locally controlled, but you just have a locally controllable head spin. Then you may ask yourself, what's the dynamic system algebra? And here it's an orthogonal algebra with 2n + 1 degrees of freedom. If you add control on the ultimate spin, the degrees of freedom just increase. And now if you shift your control from the beginning to the second, all of a sudden you now get exponentially many degrees of freedom, and the system algebra depends on the length of the chain. And if the length of the chain mod 4 is 0 or 1, then it's an orthogonal algebra, and if it's 2 or 3, then it's a unitary symplectic algebra. So this would be something like an analog or classical type of scaling. This is something like an exponential quantum scaling. And in a way, you see the orthogonal group, that's, so to say, where the fermions live in, whereas the unitary symplectic ones, that's where the hardcore bosonic systems live in a way that simply the particle number is also conserved. So it's a compact group. So whenever I write SP for the rest of the talk, it's always the intersection with the unitaries, so it's a compact part. And unless you have here, so to say, a neighboring a pair which you can control individually, you are short of full unitary control. So this example here, I think, is very nice because it simply tells you what you can simulate with what type of systems, and that these things really have experimental connection. And by the way, this is also fairly nice because you can parameterize, for instance, all the Paulis which you can have in these algebras, and therefore that also connects to the Pauli algebras in a way. Okay, so this is just an aside, and so that was on simulability. This also comes with the branching diagrams. So here we have the colored Lie algebras, and they come here with the branching diagrams. Not going into more detail. Okay, now back to our system, and we borrow a little bit from the linear type and then carry it over to describe observability on the quantum part. In linear systems, you have this type of equation of motion, and you have an observation part which usually goes like this. And then classical linear control theory by Kalman simply tells you that the rank here of B multiplied with A and all the powers of A up to n-1, if the rank here is full, then you have full controllability, and dual to that, if the rank of this observability Kalman matrix is full, then you have observability. So that's a classical result. Now, if we have an observed bilinear system like this, where we do not change the control, but simply keep it constant, then it's such that such a system here is observable. Here we already take this very special form of the scalar product to be compatible with what we have in quantum mechanics, where this here simply is the Hilbert-Schmidt trace with the observable and the state. Then conventional wisdom tells you that here, if this matrix here has full rank, then there is dependent on U. If there is such a U that this rank here is full, then the system is observable. That's a technicality which you might forget. It's simply what inspired Alessandro, who is one of the key figures in early quantum control, to simply define something like an observability space, which, if I hadn't shown you the previous slide, would simply fall out of the blue. And this simply means that if you have concatenated Lie brackets of the traceless part of your observable with elements from the control algebra, then this is the observability space. And if this observability space is the full Hermitian space, then it's informationally complete and your system is controllable. Yeah, and for the specialist, the observability space simply is a vector space that comprises this k-orbit of the observable. And now a system is defined to be observable by an observable C if the traceless part of any pair of density operators taken over the entire time trajectory, the entire orbit, if the expectation values are the same at any time, then from this, in a system which is observable, you have to conclude that the two traceless parts of the density operator were the same. So an observable system separates points. Yeah? It's a little bit of an injectivity picture. Yeah? If initially the two density operators were different, then they cannot share the same expectation values for all of their time trajectories under the dynamics of the system. Which simply means that the observability space up to a factor of I simply coincides with all the skew Hermitians. And of course, now you see the symmetry argument. For this, we have a symmetry argument, second order symmetries, and therefore it's exactly the same argument which one can take over to observability. Just a couple of examples before I drive deeper. So let's simply take the trivial situation of a pair of qubits which are not coupled by any type of binary coupling. And therefore you have X and Y controls on A and B. And now if you take as your observable the ZZ interaction, then you simply remain in what is called the Riemannian symmetric space, because all the binary operators here, they are on the local unitary orbit of ZZ, and you are confined to the P part of your Cartan decomposition. However, if now you not only had the binary part, but also a drift part on both of them, so the observable has legs in the P part and in both K parts, then you have full observability. So we have a very simple symmetry argument. If your system is not fully controllable, because there is a constant of the motion, you have a second chance and your observable has to break this symmetry, and then you are fully observable. That's how simple it gets. And this is, so to say, simply the highbrow way of noting this precisely. And one can, of course, also go to more complicated situations. So here we have 4 qubits. So here we know that our system algebra here would be SO2n plus 2. And again, the same argument holds. If you just have local controls on the first qubit and local controls on the last qubit, and here we have these pairwise XX interactions, and you start out with an observable which is this triple X, then you will remain simply in a 210-dimensional orthocomplemental space to SO10, which itself is 45-dimensional. Because from these triples on the orbit, you can never enter any one of those. And therefore here it's beyond Catan, because we are in a slightly more intricate situation. I'm not going to specialize any further. Okay, so what we do have is we split the full unitary algebra into a K part and an M part, the K part being the part where the control algebra is in, and then possibly in complementary invariant subspace. And by the Catan type of commutation relations, it's obvious that under commutation with K from the left, both K and M are invariant. And M is by construction the orthocomplement of K, and therefore we are in a trivial situation, which you know from linear algebra. So if we have a linear map, F, and you have an F invariant subspace, then there are two criteria. The first one is a no-brainer by construction. And if both the subspace W and its orthocomplement in V are both simultaneously F invariant, then F has to commute with P, which simply means you have an additional element in the commutant of F. And this being translated into our leaf frame simply means that you have such a splitting here in a dynamic system if the projection onto K and the projection on M are both in the commutant of ad K. So that's this corollary, which simply means if you have these types of splittings and your observable somehow sits in one of these summons of the direct sum, then you are lost, and the observable has to have a lag in all of them simultaneously to break this type of ad K symmetry, and then you are fully observable. Yeah, that's the highbrow way of putting it and exemplifying it, but this is what immediately tells you this type of reasoning. And I think that's fairly nice, because you see this reigns full observability by a symmetry criterion. And if we have these types of slices where you are in an ad K invariant subspace, and that holds for the observable as well as for the initial conditions, I write them as A, because then it connects very nicely to the C numerical range of A, which David also knows. So if this full-fledged breaking of the symmetry doesn't hold, but you have symmetry slicings, then within one of these invariant subspaces, you may take an initial condition and an observable, and for this initial condition, then your system would be observable on that symmetry sector. So if you share these symmetries with the initial condition and the observable, you simply get Kalman filterable pairs on symmetry sectors. Very nicely done by additional elements in the commutant. So that's observability. Let me simply move on to tomographiability. So this is something which now forms the bridge also to open systems, which is the perspective I want to close with. So number one, in a closed system, you may call it tomographiable if the reachable set of the initial state has a non-empty interior, which simply means you can you fill all these elements in the closed system. It will be the full unitary orbit. And at the same time, the observability space here of C is informationally complete. And then you can simply tomography such a system. And the same, of course, also holds if you extend it to open systems. Then the system algebra becomes a little more complicated. You cannot time reverse all directions. You don't have a Lie group, but in the Markovian case, you have a Lie semi-group. But the symmetry picture is the same. And now the system is accessible with respect to an initial state if the semi-group orbit has non-empty interior, which simply means it visits all the dimensions, but it doesn't visit all the density operators themselves, up to scaling. Yeah? It simply visits all the dimensions. Then it has a non-empty interior. And the observability space then has to be informationally complete. Is there in open systems also something like a symmetry condition that can be invoked? Yes. For unital n-qubit systems, one simply can work it out. And there it's such that, again, the commutant has to be of dimension 2, which I will make intuitive in a second. And beyond unital systems, so the blue part of the background ends here, if you watch carefully, and that's beyond the corollary. For non-unital systems, one might conjecture that this is the same, if and only if the commutant is of dimension 1. This is not magic, it's absolutely trivial. In coherence vector representation, the Lie algebras embracing the Lie wedges, the Lie semigroups, are simply of the following structure. If we have a unital system, then it can be block diagonalized, and actually this is a one-dimensional zero vector on the right-hand side and a one-dimensional zero row down there. So that's usually the way it looks in unital systems. In non-unital systems, you have a vector here, a non-zero vector here, and this, of course, also breaks certain symmetries. So here we have a symmetry which has two parameters. You can choose the alpha and the beta independently as scalars, whereas here you have a joint gamma. And in a way, now you see what this magic 2 of the adjoint representation really means. You see, this is the system algebra of a system, and here if this is simply one vector, then the projection on the identity simply gives you this trivial one-dimensional subspace, and therefore the projector on the vectorized identity in the Lie group case simply is a fingerprint of unitality. Because, of course, under any group conjugation, the identity is a fixed point. In the non-unital systems, the identity is no longer a fixed point, and therefore the unital symmetry is broken. That's the underpinning where in unital systems you have to count to 2. In truly non-unital systems, you just have to count to 1. And this also gives the nice justification. Here we have the structure constants of the commutator superoperator. Here we have one superfluous degree of freedom, the projector onto the identity, which is physically meaningful, but mathematically, of course, not part of the structure constants. Yeah, but it's a nice way of writing the adjoint representation in a reducible fashion, where you have the unitality here as a superfluous factor. Okay. So that's the underpinning of the theorem and the conjecture. And let me just go finally to this numerical support, because that also connects nicely to applications. So here, for a number of 2-qubit examples with Markovian dissipation, we have listed the symmetry. Here we have the system algebras, LK always meaning the full Lindblad-Kosakowski algebra, which I haven't specified. But here in this case, it has dimensionality or 225. And here we have the algebra. Here we have the dimension of the commutant. So whenever here the commutant is of dimension 2, we have the full Lindblad-Kosakowski algebra, so you are accessible, and that's, so to say, the open system generalization of controllability. Here the only fixed points would be the identity matrix, and all the rest simply travels around. If one has no relaxation whatsoever, then here this would of course just be the adjoint unitary algebra, and that's, so to say, the degeneration of an open system to a closed system, and that's of course something which you have to eliminate. So if you are in a truly dissipative system, then the previous theorems hold. If you are in a closed system, then this reproduces the result one has for closed systems. So totally consistent. Amplitude damping, of course, is the archetype of a non-unital channel. The extreme case being coupling to a bath of temperature 0, and there the identity, the maximally mixed state, would by thermal operations be translated to a pure state, which is here the final state of this type of amplitude damping. And in this case, unitality is violated, the commutant is one-dimensional. So that's the numerical support. I colored this in blue because that's cooling. So if you now confined yourself just to the dynamics of the populations, the diagonal elements of your density operator, then if you have an arbitrary dimensional system, finite dimensional system, consisting, say, of nq bits, or also nq trits, or also just one big blub 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 q trit, out of which at least 2 levels are coupled to a bath of temperature 0, and you have unitary control on top of this switchable coupling to a temperature 0 bath, then the theorem says that if this bath is of temperature 0, then the reachable set of just the diagonal elements of your density operators are just in the usual polytope given by the populations, where the trace condition, of course, eliminates 1 degree of freedom. And if you can get all diagonal elements under this type of thermal consideration, of course, by full unitary controllability to every set of diagonal states, you always get the entire unitary orbit, and that simply tells you that you get full transitivity on all of the density operators, the positive operators with trace 1. And here one has the closure because it's a thermal relaxation, and at times you might have to wait for thermal equilibration. That's the utmost you can get under Markovian situations. Let me simply give you the practical upshot. And I'm going to an experimental example to conclude in a second, and that's the end of the talk then also, because this means that for any pair of an initial state and a final state, density operators, if you have a unitary controllable system with a switchable coupling of 2 levels to a bath of temperature 0, then you can reach any target state, which also means if you have a non-Markovian process connecting row 0 with row target, there is always a Markovian experiment that connects the same initial state with the same final state up to closure. Yeah? In this situation, by non-Markovianity, you can't gain anything unless something falls from the closure into the interior, which simply means you could possibly do it faster in a non-Markovian way than you could do it in a Markovian way, but the reachable set closure is the same. So don't overestimate non-Markovianity. Yeah, an experimental setup simply is the following. It's this type of superconducting qubits, Gmons, which here in this preprint we took in the parameterization from the then Google group of Martinez, where exactly one has full unitary controllability, and the specialty of the Martinez group is that you had a modulatable, fast switchable coupling to an open transmission line, which here mimics a temperature 0 bath. So in this type of setting, you exactly have switchable couplings to a temperature 0 bath, which simply means that in this experimental setup, any initial state can be transferred into any final state. Yeah, and that also goes with coolability. So Barbara Kraus might talk on this. And in this, so to say, bath-enhanced type of cooling procedures, you can also outperform algorithmic cooling, in particular when the dissipation doesn't commute with the coherent controls. Okay, let me conclude, and I'm going to conclude in 3 steps. So in closed, coherently controlled systems, if your system algebra in the adjoint representation has symmetries which are spanned by the identity and the projection onto the identity operator, so you count the symmetries and you arrive at 2, then your system is fully controllable. Dually, if you have a closed system with coherent control and an observable C, you simply check the joint commutant to the adjoint representation of K. So here I should have written ad K. And for full observability, simply you count again the number of projections. And if they are trivial, then your system is observable by an ad K invariant support. In open systems with coherent control and constant Markovian or unital or non-unital Markovian noise, again, you count the symmetries to the system algebra, and in the unital case, if it's 2, then you are accessible. In the non-unital case, if the dimension of the commutant is 1, you are also fully accessible and therefore also tomographiable. So that's the joint sum up. Thank you very much.